I want you to appreciate this kind of thing. Don't worry about this, you know this already. Okay, this idea of slicing things up and adding them together, which we've talked about a few times. Okay, just appreciate this and appreciate the versatility of this, okay? So what we talked about initially was we drew a curve like that and we said let's add up all these sort of signed areas of these little slices, add them up, take the limit, and we get a definite integral. And that tells us what the signed area between the curve and the axis is. Okay, now again, humor me, I'm going to talk about infinitesimally thin slices and adding those up, and that's a shorthand for talking about adding stuff up and taking a limit. Okay. All right, so again, we did this when we talked about signed areas between the curve and the axis. We then did it again when we were talking about areas between curves. And again, I just want you to appreciate how versatile this is. So, if this thing was a velocity time curve, okay, we talked about how this was the displacement over that sliver of time, and if we add up all those, we get the net displacement. Okay, and every time I say that, think about that net change interpretation thing. Think about how definite integrals of derivatives can be interpreted as net change. So make sure you see some of that when you practice. Okay, so if this was velocity time, we get displacements in here, we add them up, we get the net displacement. We talked before, if we take the absolute value of this thing and we look at speed, and we look at those slivers, and we add those up, we get distance traveled. Or if we look at unsigned areas. If this was acceleration against time, then each sliver tells us how much velocity changes. Okay, so each sliver's area tells us how much velocity changes, and so if we add up and we integrate, we get the change in velocity. What else? I talked about areas between the demand curve and the price line, okay, and that was a similar-ish thing, and that told us about consumer surplus. And notice there was no mention of time there. It was a price-quantity curve. Flow rate. Okay, if this was volume flow rate against time, each sliver would tell you how much volume got added or taken away or whatever in that sliver. Okay, and if you add up all the signed areas, then you get the change in volume, net change in volume. Similar things for heat flow. If this was the growth rate of the population over time, okay, the signed area of each sliver tells you the change in population size over that sliver of time, and as you add up, you get the net change in population size, which is a definite integral. Just two more. If this was linear density, so you know about mass density, okay, so this was linear mass density, and obviously it wouldn't be negative, so it would have to be positive for that. And we add that up, we get the mass. Okay, if it was charge density, add up, you get charge. Okay, if it was probability density, which I brought up once, add them up, and you get the probability of, let's say, a random variable being in a certain interval. So this turns up a lot. And finally, force. So if this was force, and this was position, and we look at a sliver, that sliver tells us how much work was done moving that object over that sliver of displacement. And then if we add everything up, we get the amount of work done moving an object. Okay, so this shows up a lot. Every time you want to slice something up into tiny little pieces and add up, you get something like a Riemann sum or a definite integral or something like that. And you may remember, you can ignore this for now. What do you see that? Okay, you remember I brought this up. You guys are going to talk, if you take 128, or if you're just interested, you're going to talk about volumes of, what is it? Volumes of solids of revolution, areas of surfaces of revolution, and lengths of curves. And to do that again, you chop up, approximate, take a limit, and again, you end up with a definite integral. Final example of this type. I used to be in electrical engineering, so this mattered. We know what the electric field due to a point charge is, okay? And there's a nice equation for that, essentially called Coulomb's law. Suppose you have, instead of a point, you have a charged ring, okay? So the ring has charge, and you want to know what the electric field due to that ring is. What do? Well, you chop it up into little tiny pieces, okay? Each one acts like a point. You calculate how much electric field is due to that point, okay, which you can calculate using the equation you have, and then you integrate over the whole ring, and you use symmetries to make your life easier, and you wind up with the electric field due to the ring, okay? Then if you're interested in the disk, what do? You break the disk up into little tiny rings, and you add up the effects of all the rings, okay? So this stuff shows up over and over again. This slicing thing is incredibly important, so don't lose sight of the versatility of the stuff we're talking about. That's all. And if you like to look at derivatives and integrals, look at it. Okay, these are Maxwell's equations, incredibly important. Modifications by Heaviside, who we've mentioned before. And these tell us things like how electricity, magnetism, light, radio, all those things work. Okay? And everything there essentially is either a derivative or an integral.